Earth science time. Oh, whoa, let's start over. Earth science time. Today we're talking about, I think we'll call this measuring Earth's past. We're going to talk about more specific things than that, but measuring Earth's past. And there's a couple different ways that we do that. We'll talk about primarily, there are two main ways. Can you think of what they are? What are the two main ways we learn about Earth's past? Rocks and, you about said it, fossils, rocks and fossils. So those are actually, let's just do that. Measuring Earth's past, let's have this half of the board be rocks and this half be fossils. That's a simplification, but that's kind of, well, to some extent, that's what teaching is simplifying things. And so it's much more complicated than that, and you'll see it gets much more complicated than that as hopefully I can keep it together and not have this end up as chaotically as sometimes it does. Sometimes it really looks like the crazy guy from the movie with like the strings attaching pictures and all that. I hope I can keep it better organized than that, and this is the first step of that, is organize it into rocks and fossils. It does get quite a bit more complex, but we're here to talk about a survey level of the basic stuff. The objective today is analyze structure and function in fossils and apply to Earth's past. Analyze. I realized before I started this that I haven't written the objective for the last 4 videos I have done for different classes, but for you guys, you get the good one. Analyze structure and function of fossils and apply to Earth's past. Which do you want to start with? Well, go from left to right. Let's do the rocks first. That's actually, I'm glad you said that, because that's what I was about to say. So let's start with rocks first, because they tell us a part of the story that if we only analyze fossils, we don't usually get. And that is that we are going to talk both about what we call relative age dating and absolute. I'm going to put this a ways down here because the relative one will take up more room. Absolute age dating. I'm going to hand out this international chronostratigraphy chart. I wonder if that's showing up on the, well, now that maybe it is, but I'm not in it anymore. Well, hopefully you can see that. If you need to look at that, you can pause the video. I'm going to hand this out. This is, as it says, a chronostratigraphy chart. We're going to talk about that in a second. Would you mind holding on to one for Will? Thank you. So we have here, this is a kind of complex looking chart. Do you see the complex looking chart? Colorful, but complex. What do you think is the oldest piece of Earth's history on this chart, if you had to guess? I mean, just looking at what we've got here, looking at the columns that we have, each column is labeled, has little columns within it, and they say eonothem or eon, erathem or era, system or period, series or epoch, stage or age, and then something called GSSP, and then numerical age. You see numerical age there? We're looking across the labels on the top of the columns here. Do you see here where it says numerical age? What does numerical age mean, probably? Age in what?
Age in how many years?
There you go. How many years? Age in numbers. Numerical meaning refer to number. And then it says MA. So when we talk about Earth's past in general, we have this system that we use. Part of the vocabulary that we use to talk about Earth's past is we talk about it broken up into giga-annum, GA, mega-annum, MA, and kilo-annum, KA. Do you remember these, Cody? You weren't here, Eli, when we did this, but do you remember these from 8th grade science? Kind of. You remember maybe that they exist, but not necessarily what they are. If you had to guess, so let's start from the bottom. How many would be a kilo-annum? You're probably familiar with the term kilo. Yeah, kilo-annum is 1,000 years. What about a megaonnum? Can you guess? Million years. Yep. I'm running into my little guy here. Bye. 1 million years. And gigaonnum then? Billion years. Billion years. You can go back up here, little guy. There we go. So we use those abbreviations. And so this, the numerical age column there is in megaonnum. And it says the very, very top one on this left column, as you look at it, the very, very top one, do you see what it says right underneath numerical age? What is the very, very top, very tiny little line there? What does that represent? The very top of this column of numerical age. On the left column, which is the most recent column, like the top part of that table, underneath where it says numerical age. What's the very, very, very tip top of the whole thing? Yeah, and then there you see very top line relates to the present. So we have the top line here is the present, and then these basically, this column stacks on top of this one, that whole thing stacks on top of this one stacks on top of this one, and so all the way back in time, we get to here, right? The very bottom of the last column says how much. So it was present at the very top of the first column, the very bottom of the last column says about, that's a little squiggly line, 4,600 megaonnum, right? The heading of the column is megaonnum. And so 4,600 million years is 4.6 billion years, and that's the very beginning of the Hadean. And so that's, the physical evidence suggests that that's when the Earth basically formed out of the void, when it coalesced from meteoric particles. And so throughout all this, we have Earth's history coming from, starting here in the deep red Hadean, which, by the way, means like hell. That's what that word means, because Earth was almost certainly, evidence suggests, hot, all molten rock. Very little else besides molten rock. So Hadean, going through it, we go up this column. We're going forward in time. So go up this column, then up this column, then up this column. Here are dinosaurs. Here there be dinosaurs, and then up this column, right? If Eli, if you remember your lab that you did with Will, you had these layers that you built out of clay, and each layer, the older layers, had certain things in them, and then as you got to new layers, you got to the dinosaurs here, and then you got mammoths, and then people, and then I think you even built skyscrapers on your top layer. So it's organized in that same way, because geologists love to have things organized from oldest on the bottom to youngest on top. Why? Why do you think that is? Why do geologists love to have it be that way?
So it's in order because oldest is before the youngest.
Exactly. Oldest before the youngest, and in geology that's on the bottom. Why? Because that's how rocks are deposited. And that's actually one of our principles of relative age dating we have here. The most basic one is called superposition. In an unoverturned sequence of rocks, that means in rocks that haven't been flipped over, or sideways, or toppled, or whatever, in an unoverturned sequence of rocks, the oldest are on the bottom. And this applies to other things in your life too. Here's a new one. I usually use laundry or pizza or cake, but here's a new one. If you go through your camera roll on your phone or on your Google Photos, as you go back in time, you're going down, right? As superposition, the oldest photos are on the bottom. I can scroll all the way back in my phone to 2007. I've got pictures from 2007 on there. The oldest ones are on the bottom. The examples I usually use is if you have, you guys probably wouldn't because you're both decent human beings, but if you ever had a pile of laundry in your room, where would you find the oldest laundry in that pile? On the bottom. So, and here's what you ask, well, couldn't someone come in and flip the laundry pile over? Well, of course, and that's why we say in an unoverturned. So if nothing else has happened, the oldest stuff is on the bottom, and that applies to rocks. When we look at a sequence of rocks, we find that the oldest rocks are on the bottom. That's one principle of relative age dating of rocks, what we call the rock record. When we look at Earth's history in the context of rocks, we call that the rock record. Can you guess what we call it when we look at Earth's history in the context of fossils? The fossil record. Right? It's a recording of Earth's history as laid out by fossils or as laid out by rocks. Another principle of relative age dating, that, by the way, relative age dating means when we relate things. Relative age dating is not just when you see a cute girl at the family reunion. That's the joke I always make. Sometimes people laugh at it. It's not It's not an appropriate joke. But it's not when you see a cute girl at the family reunion. It's when you relate ages together. So it's not, in the other example I always use is, it's not Eli is 15, 14, and Cody is 17. It's just Cody is older than Eli, right? We're not talking about this rock is 300,000 years old and this rock is 750,000 years old. We talk about this rock we know it's older than. That's what relative age dating means. They're related in that way. So superposition is the first principle of that. Another one is original horizontality. Just from context clues, can you guess what original horizontality might be about? What do you think? Original horizontality. I'll give you a sentence frame. Rocks laid down are blank, blank. Blankly blank.
Rocks.
Laid down. So when rocks are laid down, when rocks are spread out on the surface of planet Earth, through whatever method, lava, rock slide, doesn't matter. When rocks are laid down, they are freely originally horizontal, right? They lay down, they're originally, when they're first laid down, they are originally horizontal. So later, can we see layers that are topsy-turvy like this? Yeah. Do you still have that pile of clay that you guys made yesterday? Is that still in there? Or do you guys take it apart? Okay, well, that's just because I actually would have worked great for this. But when you laid them down, they were horizontal, right? Could you later have like something happen where it becomes a hill? Sure. So like they look like this originally horizontal, and then maybe later, so that's time one, maybe later they get this like other stuff going, and we can see that this hill, this pushing up must have happened after the rocks were laid down because they were originally laid down horizontally. Okay, another principle is cross-cutting relationships. Cross-cutting relationships. If something cuts across layers of rock, the rock had to exist first. What are some things that could cut across rock, do you guess? How could something cut across this layer of rock? Other rock, yeah. What we call in igneous geology, we call this a dike. So maybe magma cracks up into there and squishes up into the rock. Well, guess what? That rock had to exist first before this thing could cut across it, right? Something that cuts across all these layers of rock. Or another one that happens a lot is a fault, a break in the rock. The rock had to be there first before that fault could be there. That's called the cross-cutting relationships. And the last one is inclusions. Included materials are older than, I'll just put the rest. Effectively, if we have a rock here and it has chunks of other rock in it, maybe it's even made out of chunks of other rock, those chunks had to exist before this rock could be that way. The chocolate chips in a chocolate chip cookie had to exist before you could make the chocolate chip cookie. Does that make sense? The cherry pie, the cherries that you put in the pie had to exist before the cherry pie did. And all of these, when we talk about them, they seem kind of course, like no-brainers. And the trick comes in being able to apply them to a specific sequence of rock. That's something that you'll do on your chapter review and something you'll do on your test. You'll be tested over is, here's a sequence of rocks. In what order did these things happen using these and the clues that you have? It's kind of like a little mystery game. I really enjoy. I think in the same way that the New York Times has a crossword puzzle, the New York Times could have, here's a stratigraphic column. In which order did these rocks come about? It's a nice little logic puzzle. So that's relative aging. That's how we use rocks to tell which rocks are older. So we could go out now to that butte over there. What do you call those buttes that way? These ones are Saddle Rock and Lover's Leap. What do you call these ones? Crow Butte. Okay. So we could go over to Crow Butte right now, and we could apply these principles. And we could say, well, where in this sequence of rocks, right? Crow Butte is made up of different layers of rock, and we would see that as we got closer. Where are the oldest ones? On the bottom, right? If we saw a place where there was some rippling in the rock, we would know that they were originally laid down horizontally. If we saw a place where perhaps an insect burrow cut across several layers of rock. Well, the rock was there first, and then the insect burrow happened later. And if we see a rock made of other things of rock, a rock made of chunks of other rock, we know that those rock had the things it's made of had to exist first. It doesn't tell us how old is it in years. You're 14, you're 17. It doesn't tell us that. It tells us these rocks are older than these because. So for how old are they, we use absolute age dating. And there are methods. Your book talks about dendrochronology and varves, which are ways to do absolute age dating. But the main one is radiometric. Very, 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 very reliably, as radioactive particles decay, they do so on average at a consistent rate. And measuring the ratio of parent to daughter isotopes, ratio of parent to daughter isotopes in rock, we can tell how long that rock existed. To be more specific, when it's usually igneous rock. When igneous rock crystallizes from magma, it separately crystallizes. Zirconium crystallizes entirely as zirconium. And some of that zirconium might be radioactive. And when we later look using X-ray diffractometry into that rock, and we see that this much of the, and we use mass spectrometry too, we see that this much of it is still zirconium and this much has decayed. We can see, well, we know how fast zirconium decays. We can see that this is, let's say, 60% zirconium and 40% its daughter product. And so we know such amount of time has passed. And when I say we know, I should say evidence suggests this much time has passed. But then we take that reading in relationship with other readings from other rocks. We use this evidence and we use fossil evidence, and they all point to the same thing. And so we can fairly definitively, nothing's definitive, nothing is always absolutely correct, but we can have three separate pieces of evidence that have no reason to agree, and they all agree, and they say this rock is whatever, 360,000 years old. And so we can say, without the shadow of a doubt, that this rock is 360,000 years old. This is the main tool of geologists to tell the absolute age of rocks. Now, we can't do this with all rocks. If you think about, we haven't talked about the different types of rocks. I've said the word igneous a couple of times today. But you probably remember from 8th grade science that sedimentary rocks are made of other rocks. So could we do this dating with sedimentary rocks? Well, not very effectively, because it's actually just chunks of other rocks. And so what we would find in radiometric dating those is how old those crystals are, which might not tell us how old the sedimentary rock itself is. And so for that, we use a combination of relative age dating, absolute age dating, and fossils. And that's the key, is that you can find a lot of stuff online, in books, anywhere, about how this isn't an effective tool because of these problems with it. But that's never the whole story. We use this in conjunction with other tools, just like a good carpenter, right? A good carpenter doesn't only have a saw. He also has a plane and a wood chisel and all these things. You use it in combination with other tools, and you get a more appropriate answer. One of those other tools is fossils. Fossils are about probably the coolest thing in all of earth science, in my opinion. Other people have different opinions. But I think fossils are just about the coolest thing. So give me a real quick definition of a fossil. You know what a fossil is, but give me a definition I could write on the board.
It's shaped like a bone.
Okay, not always, but yeah, it can have bones. It can be shaped like, I'm glad you said that. I'm actually going to put that up there. Shaped like what? Not always bones.
Shaped like,
what do you think, Cody? It usually is made of rock, so let's put that in. Shaped like something made of rock, and that's like occasionally, there are exceptions, but shaped like, what is it shaped like though? It is rock, almost in our most common understanding of it, it's rock, but it's shaped like what? I'll put remains, but of what? I think you're missing the very obvious key point. The remains of what? What is a fossil? It has to have been a organism. There you go. Remains of organisms. That's why it's important. That's why, as far as we know, they're unique to Earth. They're a very, very valuable tool in earth science, but as far as we know, they are, I should have switched this to picture-in-picture a long time ago. As far as we know, they're unique to Earth because we only see life on Earth that we are fully aware of. I'm really glad you said shaped like remains of organism, because they are not always the remains of organisms. Again, there are exceptions. Excuse me. There are some fossils that actually are the remains of organisms. But one definition of fossil is that it must be greater than 10,000 years old. So you can't just have like a dead raccoon. Even if the dead raccoon is mummified, it's not fossilized. Like you find a dead raccoon in your crawl space, it was probably alive 2 years ago, it's not a fossil. Fossils by definition, or by most definitions, need to be greater than 10,000 years old. But they are shaped like the remains of organisms. They're not always, and in fact they're very seldom, the actual remains of organisms. If they are, we call them original hard or original soft parts. Very rare. Extremely valuable, and I don't mean monetarily, although sometimes they can be monetarily valuable, but they're very valuable in earth science because they tell us a lot about that organism. And that's the key of fossils. They tell us about Earth's past by telling us about how life was, how living things were back then. And if we find original hard parts or original soft parts, that is the actual stuff the organism was made out of, that's very valuable because it tells us a lot about them. Another thing that they can be, well, you tell me, Cody, because this was your lab. So we could have the actual remains of the organism. Very rare because it's 10,000 years old. What else could we have that are fossils? Like what other kinds of ways can a fossil be made? Okay, there we go. So mineral replacement. This is probably the most common way that, at least that we think about fossils. It might not be, in the strictest sense, the most common kind of fossil that can be found. But mineral replacement is when everything is full of holes, right? If we look at the microscopic level, even what seems to us to be a hard bone in your example is actually full of holes. Right? I draw the circle like I'm magnifying it, and obviously these holes are not to scale. The bone is full of holes, and under certain circumstances, by the way, only about 0.1% of organisms that die ever get fossilized. In certain circumstances, burial, especially rapid burial, those, right, it's buried now in this pink rock, and now those holes get full of the rock, right? And then over time, the rock maybe erodes away, and the bone certainly does. The bone decays. Living things decay. That's the thing about life, is that it dies. And so what's left is this pink rock that has eroded away, and now it's in the shape of the bone, shaped like a bone. It is not a bone. No molecule of this is the same as it was before, but it's still shaped like it because of this mineral replacement. And so we have the shape of a bone without it actually being bone. And you can see how this is valuable because this is rock. This will last as long as rock does, right? This is how we have fossils, for instance, of the dinosaurs. To my knowledge, well, actually there are a few exceptions, but almost all of the dinosaur fossils are this, because 65 million years ago the dinosaurs died. They were around for maybe another 65 million years before that. That's a very long time. No, it's very difficult for living matter to still be around after that time. I mean, it's dead, but it's very difficult for matter that was once alive to be around at that point. But when they're replaced by the rock lasts a lot longer. If you go to the Museum of Natural History in Denver, or when we go to the museum and we see a mammoth, we're not actually seeing its real bones. We're seeing rock and the shape of its bones. Now, does that make it less valuable? Again, not monetarily. Does that make it less scientifically valuable? Not really. I mean, it's actually, in a way, it's more valuable because it lasts longer, and we can study it now, even in a much later time. What other ways? You had another one. Mold. In the English spelling, or in the American spelling, M-O-L-D, in the British spelling, M-O-U-L-D, and cast. And this one, a similar thing, but what happens in this one is that there's some soft sediment, like your clay, and the organism is pressed into that clay, or maybe just its footprint is pressed into that clay, or whatever, is pressed into the clay, or whatever soft sediment. That soft sediment hardens into a rock, and now there's a hole left in the shape of the organism. But kind of like in this example, the rock is a rock, right? It lasts for a long time. And then sometimes that rock gets filled in with other rock, and that's called a cast. And so a mold is a negative impression. That is, it's a hole in the shape of the organism. And a cast is a positive impression. It's the filled in hole that then hardens, and it comes out in the same shape as the original thing. Oh, I almost forgot something else. these are fossil preservation methods, like ways that fossils can be preserved, but there's a difference between what we call trace and body fossils. Trace and body fossils. So trace fossils are fossilized behaviors. Like, they're not the actual parts of the organism's body. Again, not necessarily just that they're the same stuff as, but they're not even representations of its original body. But there might be like a footprint, or a nest, or a very usual one is coprolites, which is poop. I don't like to say that word, but it's dinosaur or other organism feces, and that being fossilized. So that's not an actual part of its body, but it's a fossilized behavior. Whereas body fossils, I'll just put this, body. Body fossils are actual fossils of its body parts. And so fossils are neat. They show us how organisms look, which is important. But they also show us things like its stride length by showing us its footprints, or they show us its mating habits by showing us its nest, or its digestive habits with its feces. So we can learn a lot about not only how organisms look, but how they even behave through fossils. And that, in combination with absolute age dating of rocks and relative age dating of rocks, tells us about the world as it was. Because why? The main principle here is what we call uniformitarianism. I'm going to write that over this. Uniformitarianism. This was one of your vocab boards. Uniformitarianism. What does that mean? You remember from your vocab?
Geological processes occurring since Earth began.
Geological processes today have been occurring since Earth began. What that means is that if we assume that the stuff that we see going on in the world today, erosion, deposition, life, right, cross-cutting phenomena, if we assume that stuff that is occurring today, that we can witness today, has been occurring for all of Earth's history, well, now, using that link between today and the past, we can now have a greater understanding of what Earth's past was, right? If we pretend like the stuff that happened in the Earth's past was a one-off, that it only happened once, then that makes it seem like, well, really, we don't know what's going on, that we can't have evidence to suggest it. But if we realize that the things that are happening today have been happening, and we apply the stuff that we can see today, because guess what? The point is, we can't go back in time, right? The greatest tool of the geologist, just go back in time. No, of course not. That's impossible. We can't go back in time. We can't go back and watch what the dinosaurs were doing. We can't go back and see what the rocks were like 360,000 years ago. It's impossible. So what we do is we look at the world around us as it is today, and we apply that to how it might have been. We use it as evidence for how it might have been in the past. For instance, in this area, a lot of the rocks are volcanic ash. Now, we can't go back in time and see the volcano, but we can go to a place in right now time where there is a volcano, like Hawaii, and then we can learn about volcanoes there, and we can apply that knowledge to the volcanic rocks that we see here, and that helps us learn about them. Does that make sense? That's called uniformitarianism. And that's the principle over all of this, over all of measuring Earth's past, is uniformitarianism. Do you have questions about any of this? Fossil record and rock record. Those are the main tools of learning about Earth's past.